Okay, we just are finishing up the previous problem from number 35, in which we had this equation, we drew off the half reactions for it. We were able to pull up chromium's reduction potential from the back of the book. We always use just the reduction potential. It doesn't matter if it's at the cathode or the anode, we always use reduction potential. So in other words, the gaining of electrons. We put it into this equation and we can see the positive value for that. The last part here is to sketch a voltaic cell, labeling the anode and the cathode and indicating the direction of electron flow. All right, so I'm just going to draw a really simple picture here. Got this thing going on. I've got a salt bridge. I've got some metal over here, some metal over here. They're connected by a voltmeter hanging out right there. Over on this side here, I'm going to have well, I don't actually know that yet, so let me hold off on that. I've got some thallium, 3+, and I've got some chromium, 3+. Now, as far as what was going on here that we could figure out already based on the values that we have, we had thallium that was gaining electrons, so that's where reduction takes place. So this is where the thallium was. That's where reduction's taking place, and reduction always happens at the cathode every single time. And then therefore the side's pretty easy. This is going to be oxidation because we are losing electrons, and that is the anode. And again, these metals represent, they probably are just platinum in this case because everything is staying in solution. I don't have any metals in which I'm having a reaction, a separate reaction taking place there. So these are just platinum electrodes in which electrons are being gained or lost. Now also, therefore, what you must have in the solutions is you're going to have some chromium 2+, and over on this side you're going to have some thallium 1+, which is going to be, both of these are going to be present in the solution. Okay, that one's done. Let's do one more example, and then we'll go back over to the notes. You have a 1 molar solution of copper nitrate. It's placed in a beaker with a strip of copper metal. A 1 molar solution of tin sulfate is placed in a second beaker with a strip of tin. Salt bridge connects it, the wires, voltmeters, yada yada. Got it all. Okay, with this, which electrode serves as the anode and which serves as the cathode? At the moment, I have no idea. So I have to go in the back of the book, Appendix E, and see, well, what's going on with copper 2 nitrate? Let's pull up the reduction potential of copper 2. This would be that half reaction. The value that goes along with that is positive 0.337 volts. And if I look on what's going on with tin 2, every time it's going to be a reduction potential. Its value will be negative 0.136. And again, this is how these two guys behave with hydrogen gas or hydrogen ions, which is a zero value, 0.00. So that's how they behave with each other. Now, based on this difference here, as we mentioned a couple times previously, whichever one is more positive, the more positive reduction potential happens at the cathode. And the more negative or less positive happens at the anode. So which electrode serves as the anode and which is the cathode? So I will say the anode, which is the less positive of the two values, is going to be the tin. So tin will be the anode. And the cathode is going to be copper, the more positive of the two values. Which electrode will gain mass and which one will lose mass? So if oxidation occurs at the anode, oxidation means losing electrons. And if you're losing electrons, that means that electrode is going to corrode and the metal will turn into ions It will react and turn into ions and go into solution. So the tin electrode itself will lose mass. And the copper electrode will gain mass. And again, the reason why that gains mass is because at the cathode, reduction occurs, and reduction is gaining electrons, and those electrons will collect on the plate. The ions will gather there and form copper metal. Write the equation for overall reaction. So the reaction is going to be having copper ions trading electrons from the tin metal and forming copper metal and tin ions. If you want to push this one step further, we could talk about some electrons on both sides just to show the exchange of those electrons. Many times I don't put that in there, but now I can see that there's two electrons changing places. What is the EMF, the electromotive force, generated by the cell under these standard conditions? Here we're just putting in the math. So E for the cell is based on positive 0.337 minus a negative 0.136 volts for both of them. Therefore, you get a positive value, 473 volts. There you have it. Done. All right, let's bounce over to some notes. This is going to be one of those kind of putting everything together type problems. We'll get it set up, and we probably won't get all the way through this just because of the time we like to cut these off for. This is one of your homework problems actually as well. It's number 27. Okay, for this problem, we're given a drawing and an equation. The equation happens to be iron solid plus some silver reacts and produces some iron ions and some silver metals. And if I look in the back of the book, the reduction potentials for silver are positive 0.80. That's fairly high. And for iron, it's negative 0.44. Okay? Well, based on this fact that silver is more positive, and we can actually see it written out here, silver is gaining electrons and iron is losing electrons. So I'm just going to kind of show what's going on here. With the silver, it's gaining 2 electrons, and iron is losing 2 electrons. It has to be the same number, no matter what. It has to be the same number. Okay, so this little part here first, we're going to make the drawing based on what this looks like. So another one of these electrolytic cells. I should say voltaic cells, excuse me, voltaic cells. Little voltmeter thing here. We can do the math on that a little bit later. I don't think we're there yet. Salt bridge. And that's simply going to be some sodium nitrate. We'll talk about directions later. Got some iron solution. It's always 1 molar. Some silver solution over here. This happens to be iron metal, and this happens to be silver metal as well. Okay, I think I got everything in place here. Given this understanding, based on the equation we have written here, we've got some math. Our first question that we have, I'll go ahead and put it over here. What is being oxidized and reduced? So based on really the two metals, what's being oxidized and what's being reduced? Well, I can kind of look here and say oxidation is losing electrons, and it looks like iron has lost electrons, and silver has gained electrons. And of course, we wrote that in here. So I think we're pretty good there. So I'm going to write that down. Iron is oxidized, and silver is reduced. Okay, that's easy. Next part, we'll do part B here, and then we'll call it quits at that, and we'll pick it up in the next lecture. But for part B, we're simply being asked to write the half reactions for that. Well, that's pretty easy. They're pretty much right here. I just got to pull them out. Iron, solid, is turning into iron ions and some electrons. Okay? And then with the silver, you're starting off with ions, and there's two of them. That seems to be gaining some electrons. I already wrote that down up above. And having this. And again, just to be clear on this again, this was oxidation, and this is reduction. So we got it. All right, so this is a good break, and we have just a few more parts to this particular question, which we will pick up in the next lecture.